This is a flow diagram of a very simple theoretical milling system. There are many different systems and most are more complex, but we will begin with this one for learning purposes. The production of flour from clean and conditioned wheat can be divided into three systems: the break, purification, and reduction systems. This chapter is about the break system. In this chapter, you will learn about the purpose of the break system, the design of the break system, how products are produced through the system, mill balance, and brand finishes. The purpose of the break system. The main purpose of the break system is to separate the endosperm from the bran and send that endosperm to downstream sections of the mill for further treatment. The break system will also generate some flour along the way. The final products of the break system are flour, particles of various sizes larger than flour, consisting mostly of endosperm and some bran, and clean bran. Break system design. The break system is designed as a series of grinding and sieving passages. The grinding is done mostly by roller mills and the sieving is done mostly in the plant sifter sections. Each roller mill has an associated sifter section within a plant sifter to receive and grade its ground material. The path through the roll and sifter together is called a passage. The break system employs a gradual separation process. Through repeated grinding and sieving cycles, the endosperm is gradually separated from the bran pieces. This helps minimize bran contamination during separation. It also minimizes over-grinding of endosperm particles, allowing larger pieces to be sent to downstream processes for more effective treatment. Toward the end of the break system, the final cleaning of the bran may be performed by machines called brand finishers instead of roller mills. First break passage. At the first roller mill in the break system, called first break, the wheat kernels are broken open. Intact wheat kernels are fed over a single feed roll to the grinding rolls. The kernels are gripped against the fluting of the slower rolls and sheared open by the fluting of the faster rolls. As the faster roll continues to spin, the endosperm is scraped away from the bran in large chunks. First break rolls have relatively large flutes which help reduce over-grinding at this early stage in the milling process. They enable particles to hide between the flutes and escape over-grinding. The stock exiting from the first break roll will ideally be mostly large bran particles and large pieces of endosperm. But there will usually be a spectrum of particle sizes, including some flour. The stock must next be sifted over a range of screen sizes to separate the particles by size. This is achieved in the first brake sifter section. The stock passes over the coarsest screen first. The large brownie material overtails to the next roll in the brake system called second brake. The removal of large brownie stock like this is called scalping. The remainder of the stock is released through the screen for further sieving through finer screens. The percentage of stock released through this screen is referred to as the release for that roll. So in this case it would be called first brake release. The release in the plan sifter is usually approximated based on a sieve test on a lab sifter. The harder the stock is ground, the finer the stock becomes, and the more stock is released through the screen. Each mill is designed so that stocks distribute through the passages in specific proportions. Each roller mill has a specific release target, so the roll gaps should be adjusted to achieve this target. When this target has been achieved for all relevant rolls, the mill is said to be balanced. Balancing the mill begins with achieving the correct release for first brake. Once first brake release target has been achieved, the split between the stock tailing the screen and the stock passing through the screen in the first brake sifter section can be considered to be optimized. This is the first step towards ensuring the stocks are distributing through the mill in the proportions that the mill has been designed for. The remaining material continues to travel over progressively finer screens, separating the stocks into different size classes. This is called grading. The finest screens are flour covers, and the stock passing through these is flour. Flour sifted out in the various plan sifter sections is removed from the milling system. As soon as it is sifted out via spouting to a flour collection conveyor. This is to prevent the flour from becoming contaminated with bran from the milling processes. The next size up from flour is known as dunst. Dunst is too large for flour, but too small for purification. This is sent to dedicated sifter sections for further sieving, or to the reduction system. The next size up from dunst is known as middlings, or semolina. Semolina can have a range of particle sizes. Semolina is segregated into various size classes and sent to specific purifiers that deal with those sizes. Second brake passage. The fluting on second brake rolls is slightly finer than for first brake to more effectively scrape off the endosperm. Finer fluting risks fracturing more of the bran to flour, but is necessary to separate a satisfactory proportion of endosperm from the bran. The stock that arrives on second brake consists mostly of large bran particles, with significant amounts of endosperm still attached. The milled stock coming from the second brake roll is segregated in much the same way as for first brake stock. Bran from the second brake sifter section is passed to further brake rolls with progressively finer fluting. Further brake passages. At this point, some systems will have passengers with coarsely and finely fluted rolls to deal separately with coarse and fine bran. Separate treatment allows more precise processing on each roll. Each new stage in the brake system scrapes the bran more aggressively to remove endosperm layers closer to the bran. Therefore, the flour towards the end of the brake system is progressively more contaminated with bran and will have progressively different qualities. This is partly because of different bran levels of contamination, and partly because the endosperm near the bran has different qualities. The layers of endosperm near the bran have different protein and mineral contents to those near the center of the kernel. Bran finishes. Towards the end of the system, bran finishes are used. These also clean the bran, but are gentler than roller mills. They consist of a cylindrical screen or cage with perforations too small to allow bran to pass through, but large enough to allow flour through. Bran is fed into one end of the cage, and beaters move the bran along the length of the cage, rubbing the bran against the cage as they go until clean bran is released at the other end of the cage. The flour released contains more bran the further along the cage it gets. There may be a flap that allows a divide to be made. Some types use vibration to keep the screen clean. Others rely on the negative pressure provided by aspiration. Screens should be regularly checked for wear. Bran finishers clean the outermost layer from the bran with less bran breakage than roller mills. This outermost layer is called the aileron layer and is the oiliest and therefore stickiest of the flours. In summary, the brake system produces multiple flour streams, which are all sent to a flour conveyor. It also produces multiple semolina streams, which are all sent to various parts of the purification system, and some Dunst stocks, which are sent to the reduction systems. Finally, it produces clean bran, which is either sent to a bran bin or mixed in with ground screenings from the screen room to form an animal feed product called wheat feed. This chapter has covered the design and purpose of the brake system, how the products are produced through the system,